Imagine you're a renowned physicist. Why is it said that humans understand less than 5% of the universe? Rather than saying we live in ordinary matter, it's more accurate to say that the world we're familiar with is extraordinarily special. In this episode, we'll discuss what the universe is made of and how much of it we humans truly understand. Since ancient times, people have been curious about the world. Many questions arise not from practical needs, but pure curiosity. Picture two primitive men, professors, if you will, smashing a large rock against a smaller one. In their language, they might call this a particle collider. Many human questions concern the fundamentals of the world, such as what is the universe made of? When a primitive man looks at a rock, he likely intuitively thinks that a large rock is made up of smaller rocks. So, what about the small rocks? They're made up of even smaller rocks. If you were the first person to seriously answer this question, you might respond in this way. You would list the entire universe in a table, with the first item being the universe itself, followed by many subdivisions, including me, you, this rock, that rock, elephants, goats, goat legs, and so on. But there's a significant problem with this method. The list would be incredibly long, as it would need to include every person, every rock, every goat in the universe. If you also wanted to express the components of these things through this list, it would be infinitely long, and of course, it would also have to include the list itself. If you decide not to list the internal components of objects, the list would become incredibly short, with only one item, the universe. This list would then be useless. More importantly, this list wouldn't help you truly find the answer to the question. A satisfactory answer should not only reveal the complexity of the universe but also its simplest principles. It should not only state that there are infinitely many things around us but also simplify them. For example, the periodic table you learned in middle school serves this purpose. People hope that everything they can see, touch, and hear is based on these basic elements from the periodic table. The principle of the universe's composition is similar to Lego blocks. Large things are assembled from smaller pieces. When we break down a large object, we eventually encounter a very simple small building block, and all things in the world are composed of this small building block. How simple is that? In fact, like Lego blocks, elements can make up many things in the universe, such as stars, rocks, dust, animals, plants, and so on. An ancient scientist might guess that there could be infinite types of elements, with rocks possibly made up of rock elements, air made up of air elements, and fire made up of fire elements. If one thinks in this way, this primitive scientist would have a very, very long list. Of course, we say this not because our universe is inherently like this. Here, we're discussing a way of thinking, a way of understanding the universe. If no other scientist told you about the periodic table, you might guess that our universe is like this. In our universe, things far, far away from us might also be like this. The actual situation is that with the development of science to this day, people have broken through the scale of the periodic table and seen the situation inside atoms. As far as we know, matter is composed of the elements in the periodic table, which are in turn made up of more basic units, such as atoms and electrons. Inside atoms, there are protons and neutrons, which are made up of up quarks and down quarks. Different numbers of electrons orbit around the atomic nucleus, and different masses of atomic nuclei plus different numbers of electrons constitute different elements. Therefore, we have up quarks, down quarks, and electrons as the three most basic elements. With these three elements, we can create any element in the periodic table. Congratulations! We have simplified the infinite universe into a list, further simplified into a periodic table, and then further simplified into 3 examples. With these 3 examples, everything you can see, touch, and smell can be built from these smallest blocks. It was not easy for humans to get to this step. But don't rush. With the exploration of basic particles, people found that there are other types of particles, not just electrons, and 2 types of quarks. Although to construct everything you can see, touch, and hear, these 3 examples are enough. However, in the 20th century, particle physicists discovered 9 other types of matter particles and 5 types of force-carrying particles, and these particles are very strange. For example, neutrinos, they are like ghosts. They can pass through lead blocks trillions of kilometers long without being stopped. This lead block is as transparent to them. There are some other examples, similar in properties to up quarks, down quarks, and electrons, but they are very, very heavy. Scientists wondered, why are there these extra particles? What are they used for? Who put them in our universe? What is the significance of their existence in this universe? We don't know these things yet. In addition to this problem, there is a bigger problem. Although the three known particles can form stars, planets, comets, and rabbits, people have found that these things only occupy a small part of the mass of the universe. Everything we know so far, including matter and energy, the ordinary matter and energy we come into contact with every day, only account for 5% of the known universe. They should not be called ordinary matter, they should be called special matter. The 5% we're talking about includes stars, planets, and everything on these celestial bodies. Apart from this 5%, there's another 27% of stuff we call dark matter, and a further 68% is something we understand even less about, which scientists call dark energy. For dark matter, we only know it has gravity, but we don't understand any of its other properties. As for dark energy, we don't even know about its gravity, just that it's causing our universe to continue expanding. Beyond that, we know nothing about it. You might wonder, are these proportions of 5%, 27%, and 68% just made up by scientists? They're not, and we'll explain later how these proportions were calculated. You see, this is the current state of human understanding. To put it in perspective, it's as if for thousands of years, people have been studying an elephant, and after thousands of years of research, we realize we've only touched the tip of the elephant's tail. Hearing this, you might feel a bit disappointed. After all these years of exploration, we know so little. But there's no need to feel disappointed. Think about it, when we were young, we often heard stories of heroes exploring the world, like Columbus discovering the Americas. But today, all continents on Earth have been discovered, and all the islands have been named. At this point, would you still be excited about exploring new continents on Earth? Probably not. But our understanding of the universe is far from stepping off the small island where we were born. Imagine if humans had only developed 5% of the land on this planet, wouldn't you, as an explorer, feel extremely excited? In fact, humans have just embarked on a new era of exploration. On the one hand, we know that our knowledge is very limited. On the other hand, we are building some amazing new tools, like large particle colliders, to reveal the deepest secrets of the universe. It's very likely that people 200 years from now will look at our current understanding the same way we look at primitive people today. Thinking about this, wouldn't you feel happy about our ignorance? Next, let's talk about dark matter. Current physicists believe that 27% of the known matter and energy in the universe is so-called dark matter. This proportion is quite scary, meaning that most of the matter in the universe is not the matter we have been studying for centuries. So what exactly is dark matter? Is it far from us? Or is it right beside us? Does it pose a threat to us? In fact, dark matter is everywhere, and right now, you are in dark matter. The discovery of dark matter comes from astronomers who found the rotation and mass of galaxies a bit puzzling. You can imagine a turntable with many ping-pong balls on it. If you spin the turntable, the ping-pong balls at the edge will be thrown off. The rotation of a galaxy is similar. Because the galaxy is rotating, the stars inside have a tendency to be thrown out. What keeps these stars from being thrown out? Of course, it's gravity. The faster a galaxy spins, the more gravity it needs to hold these stars. Conversely, if you know the mass of a galaxy, you can infer how fast it can spin. At first, astronomers estimated the mass of a galaxy by observing the number of stars in it. But when they used this number to calculate the rotation speed of the galaxy, things didn't add up. They found that the rotation speed of galaxies was much higher than the rotation speed inferred from their mass. In other words, these stars should have been thrown out of the edge of the galaxy, just like the ping-pong balls on the turntable we mentioned earlier. But in reality, these ping-pong balls didn't fly out. To make the rotation speed reasonable, scientists had to increase the mass of the galaxy in their calculations so as to hold these stars together. But they couldn't see where this extra mass came from. So they thought, if every galaxy has something very heavy, but this thing is invisible, then it makes sense, right? But this inference is very special. Astronomer Carl Sagan once said, "Extraordinary claims require extraordinary evidence." So apart from calculations, what other evidence have people found to prove the existence of dark matter? One very important piece of evidence is gravitational lensing, an observed phenomenon where dark matter bends light. Sometimes astronomers see some strange things when observing. They see an image of a galaxy in one direction. Move the telescope slightly, and they see another identical galaxy in another place. These two galaxies are identical in shape, color, and light. What's going on? Why do you see two identical galaxies in the same patch of sky? Later, people found that if there is something very heavy, and you can't see it, and it's right between you and the galaxy, then this phenomenon has a reasonable explanation. This invisible heavy chunk acts as a gravitational lens. Light is emitted from the galaxy, one beam to the left and one to the right. When these two beams of light fly past this invisible heavy matter, they are bent back and converge to a point. When this point of convergence is exactly where you are observing, you will see light coming from two different directions. That is, you see the same galaxy in two different directions. This effect is actually very common in the entire night sky, which means that very heavy matter seems to be everywhere. This is the first extraordinary evidence people have found. The second very resonant evidence is colliding galaxies. Millions of years ago, two galaxy clusters rushed towards each other and had an epic collision. Of course, we couldn't watch this collision live, because the light emitted during the collision process would take millions of years to reach Earth. When two galaxy clusters collide, their gas and dust present a spectacular sight, with huge dust clouds being torn apart. This can be described as a luxurious red performance. But when astronomers observed the collision of these two galaxy clusters, they noticed another phenomenon. Near the collision point, they found two clumps of dark matter. Of course, this dark matter is invisible. It's just that astronomers found that the light emitted by nearby galaxies was distorted by the dark matter clumps, proving the existence of two large dark matter clumps. The strange thing is that these two clumps of dark matter moved along the direction of the collision, as if nothing had happened, and passed through each other. Astronomers put this information together and reasoned out a fact. There were once two galaxy clusters, each containing some conventional matter, such as stars, planets, gas, dust, etc. In addition to these conventional matters, there was also dark matter. When the two galaxy clusters collided, most of the gas and dust collided and tore each other apart. But what happens when dark matter collides with another clump of dark matter? People can't detect anything. The dark matter clumps continue to move, passing through each other, as if they are transparent. Of course, the stars in the galaxy also pass through each other, but that's because they are too sparse in space, they didn't collide with each other. Dark matter is quite peculiar, and it differs significantly from the things we are familiar with. Here's what we know about dark matter. First, it has mass. Second, it is invisible. Third, it doesn't interact much with ordinary matter. Fourth, it doesn't seem to interact much with other dark matter either. Lastly, it doesn't hide in distant places. Dark matter tends to cluster together, forming large matter clumps, and it seems to prefer being in galaxies. We haven't found dark matter in places without galaxies, which means that you might be in the midst of dark matter right now. It's quite strange to think about something that is there, but we can't see it. This is why studying dark matter is so challenging, because we don't interact with it much. To understand this, we need to first discuss ordinary matter and how it interacts. There are 4 ways matter interacts. The first is gravity. If two things have mass, they will attract each other. The second interaction is electromagnetic force. If two particles carry a charge, they will generate an electromagnetic force between them. This force can either attract or repel, depending on whether their charges are opposite or the same. Don't think that electromagnetic force is far from our daily life. In fact, you experience this force every day. When you stand on the ground, you are not pulled into the earth by gravity because the floor supports you. What is the force that supports you from the floor? It's actually the electromagnetic force, as the molecules in the floor are tightly bound together by it, and they also repel your feet. The third interaction is the weak nuclear force, which is somewhat similar to the electromagnetic force in many ways, but it is very weak. For example, neutrinos interact with other particles through this force. As we mentioned before, the interaction between neutrinos and other particles is very, very weak. They can pass through a thick block of lead without slowing down. Although the weak nuclear force is very weak, when the energy is very high, this weak force becomes as strong as the electromagnetic force. In fact, the latest research has confirmed that it is this weak interaction that forms the electromagnetic interaction. The last interaction is the strong nuclear force, which we don't encounter much in our daily life. It is the force that sticks protons and neutrons together inside the atomic nucleus. Without it, the positively charged particles inside the atomic nucleus would repel each other and scatter. In other words, the strong nuclear force is much stronger than the electromagnetic force, as it can bind protons together. However, the characteristic of this force is that its effective range is very short. Once the distance between two protons is slightly larger, this force no longer exists. Here, you need to look at these four interactions from a different perspective. You might imagine that there are these four forces in nature. Then we humans have discovered these four forces one by one. But it's not actually like that. To some extent, physics is a bit like botany. We currently don't know why these forces exist. We just record the situations we observe and then categorize them into four types of interactions. We don't know at all whether these four forces are a unified way of interaction. We don't even know if the list of these four forces is a complete list. It can only be said that so far, we can use these four forces to explain the results of every experiment in particle physics. Now, having discussed these four interactions, we can talk about dark matter. First of all, dark matter has mass, so it has gravity. But as for its interactions, the information we can confirm is just that. As of now, scientists believe that it does not participate in electromagnetic interactions, nor does it reflect or emit light. Dark matter also seems to lack weak nuclear force and strong nuclear force. That is to say, dark matter is something that we can only see interacting with other matter through gravity, and it does not possess the other three forces. We call something with mass, matter, but we can't see it, so we call this kind of thing dark matter. At this point, a question arises: what is dark matter made of? For the composition of the entire universe, we have only studied the simplest 5%. We can't pretend to know that dark matter is composed of some kind of dark matter particle. We also can't ignore this dark matter that accounts for as much as 27%. Right? Until now, the smartest brains in the world still don't know what dark matter is. We know it exists, know its size, and roughly know its location, but we just don't know what particles it is made of. We don't even know if it is made of particles. Given that the matter we understand makes up less than 5% of the universe, we are essentially trying to generalize the composition of the entire universe based on a special kind of matter. If you extrapolate in this way, you're bound to make a big mistake. So how should we speculate about dark matter? To make progress, we need to make some guesses, draw some inferences from our existing knowledge, and finally design some experiments for testing. You might say, perhaps dark matter is composed of a type of life form we don't know about. Of course, you can think this way, but it's too hard to verify, so it's not the first choice in science. A simpler and more concrete idea is that dark matter is composed of a new type of particle that we haven't discovered yet. They interact with ordinary matter in a very weak way through a force we don't yet understand. Why do people guess that dark matter only contains one new type of particle, rather than 5, 8, or 12? This is because it's the simplest assumption, and such ideas will be tested first. If you guess that dark matter is composed of 12 types of particles, how would you test it? We can only start with the simplest assumption. Of course, it's entirely possible that dark matter is composed of several types of particles, just like ordinary matter. It's interesting to imagine. These dark particles might have various interesting interactions, possibly producing dark chemical reactions, and perhaps even dark life exists. At present, the candidate particle in this hypothesis is called a WIMP by scientists, which is an acronym for weakly interacting massive particles. The weak interaction, here is the guess that it interacts with our ordinary matter through a new force, and this interaction is very, very small, almost similar to the level of interaction between neutrinos and ordinary matter. How do we know that dark matter particles interact with ordinary matter through a new force, rather than an existing force? Actually, we don't know, we just hope it's the case, because we can't explain the existing forces, but with a new force, we hope to be able to detect it. Physicists have designed some experiments to detect this hypothetical dark matter. A classic strategy is to fill a container with compressed, low-temperature inert gas. Detectors surround the container, and if a dark matter particle hits an atom in the gas, the detector will sound an alarm. Unfortunately, so far, these experiments have not found any dark matter, not a single particle. The related equipment needs to be large enough and sensitive enough to detect dark matter particles. Another method is to use a high-energy particle collider to create dark matter, accelerating ordinary matter particles to high speeds and then colliding them together. This kind of collision can transform one type of matter into another. It's important to understand that in these collisions, particles do not rearrange internally to become a new particle, but rather the old matter is annihilated and new matter is created. In other words, you might not know what you're looking for before the collision, but after the collision, you can create almost any new particle. Today's cutting-edge scientists spend their days colliding particles in high-energy particle colliders, hoping to create a new particle that will help us discover dark matter. Another method is to point telescopes at places where we think dark matter is highly concentrated, with the nearest being the center of our Milky Way galaxy. There seems to be a large chunk of dark matter there. The idea here is that two dark matter particles might randomly collide and thus annihilate each other, generating new particles, which are likely to be our ordinary matter. If such reactions occur frequently enough, then the ordinary matter particles produced by these collisions will have a special energy and position distribution. People hope to discover this process through telescopes, but so far, no success has been achieved. Finally, let's summarize. All of humanity's discoveries and advancements so far have been unable to explain the nature of the universe, and dark matter is a very important clue. Of course, our current level of understanding is far beyond that of primitive humans. But dark matter has not even appeared in our mathematical and physical models of the universe, let alone in our textbooks. It's quite distressing to think about it. There's so much stuff in the universe, silently pulling at us every day, but we don't even know what they are. We humans really can't claim to have understood the universe. Imagine if dark matter is composed of some new particle, and we could create and control it through high-energy colliders. What would that be like? If in the process of discovering this dark matter, we discovered previously unknown physical laws, even new fundamental forces, or new ways these fundamental forces interact. What would that be like? If in the process of exploration we discovered these new forces, new particles, that could allow us to control current conventional matter in new ways. What would that be like? This is actually the greatest benefit that basic research brings to humanity. When we question what a substance really is, the question may seem meaningless, but in the process of digging deeper, we discover unexpected things. For example, by studying relativity, we developed GPS satellite navigation, and by exploring the quantum world, we developed the internet and mobile phones. Who knows how many amazing technologies and knowledge we could gain from the process of figuring out what dark matter is. That's all for this section on dark matter. In the next one, we'll talk about dark energy.